Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 9. The QR method for tridiagonal matrices. The QR iteration method, also called QR algorithm, is an iterative numerical technique used to compute the eigenvalues and, in some cases, the eigenvectors of a square matrix. The method is widely used in numerical linear algebra due to its stability and efficiency and can be applied to any square matrix, whether it's symmetric, non-symmetric, or complex. It is more efficient and converges faster, especially for symmetric matrices. It works by decomposing a given matrix A into the product of an orthogonal matrix Q and an upper triangular matrix R, and then using these matrices to generate a sequence of similar matrices that converge to an upper triangular form, from which the eigenvalues can be easily read. The QR method for tridiagonal symmetric matrices is a specialized version of the QR iteration that takes advantage of the tridiagonal and symmetric structure to make computations more efficient. A tridiagonal matrix has non-zero elements only on the main diagonal and the diagonals just above and below it. Since the matrix remains tridiagonal, this structure reduces the number of computations required for QR decomposition by avoiding unnecessary arithmetic operations. It also avoids excessive rounding errors. This approach is widely used in numerical linear algebra because it significantly reduces computational complexity while maintaining numerical stability. We consider a symmetric tridiagonal matrix. Finding the eigenvalues via the Sturm sequence can be impractical when a tridiagonal matrix is very large. A tridiagonal symmetric matrix can be reduced to a diagonal matrix by employing the QR decomposition. The goal is to decompose the matrix into the product of an orthogonal matrix, denoted by Q, and an upper triangular matrix, R. If E1 equals 0 or En-1 is equal to 0, then one of the eigenvalues of matrix A is D1 is equal to 0 or Dn equals 0. The QR iteration exploits this property of tridiagonal matrices by successively eliminating the subdiagonal elements using the following two steps. Matrix A is decomposed at every pth iteration step, as AP equals QPRP, and the matrix AP plus 1 is constructed as our PQP, where A0 equals A is the original symmetric tridiagonal matrix. QP is an orthogonal matrix, and our P is an upper triangular matrix. The decomposed matrix is expressed by where A0 equals A and AP denotes modified matrix, and superscript P denote the modified matrix elements at the pth iteration step. The objective is to apply a series of orthogonal transformations to obtain a sequence of similar matrices AP that, for sufficiently large P, eventually converge to a diagonal matrix A infinity, whose diagonal elements are the eigenvalues of A. After every similarity transformation, not only the tridiagonal structure and the symmetry property, but also the eigenvalues of A are preserved. We begin by decomposing A1 equals A as a product of an orthogonal Q1 and an upper triangular matrix R1, which is expressed as Q1R1. Next, A2 equals R1 times Q1 is constructed. To generalize, we define two matrix products. AP equals QP RP and AP plus 1 equals RP QP for the pth iteration step. Since QP is orthogonal, making use of RP equals the product of transpose QP-AP, we find. By defining proper RP and QP, the matrix AP plus 1 is assured to be tridiagonal. The following is a matrix representation of the rotation of the k-1th and kth axis about the origin of the coordinate system by the angle theta. Due to the symmetry, we deal with the diagonal and subdiagonal elements only. The decomposition is carried out by a so-called rotation matrix. We define an orthogonal matrix, an identity matrix whose k-1th and kth rows and columns are modified for an arbitrary rotation angle theta, as shown. The right multiplication of the transformation matrix P sub k, k plus 1, with an arbitrary matrix M affects only the k-1, th and kth rows and columns. We adopt rotation sign and cosines as S and C, respectively. Here, the QR iteration steps and development of a general algorithm are illustrated for a 4x4 symmetric tridiagonal matrix A. For the first rotation, the matrix P12 is chosen such that the product matrix P12 AP yields 0 at the second row, first column. The product matrix P12 A0 yields. We should set second row, first column to 0, and note that C1 squared and S1 squared equals 1. The rotation cosine and sine are obtained by solving the two equations with two unknowns, which result in substituting the rotation cosine and sine values yields, where the following quantities are used. The second rotation matrix P23 is chosen such that the product of P23, P12, and AP gives 0 at the third row, second column. The matrix product P23, P12, AP can be explicitly written as follows. We set third row, second column to 0. And note that C2 squared and S2 squared equals 1. The rotation cosine and sine are obtained as follows. Substituting the S2 and C2 values found, we get where D2, E2 at the second step, and F2 have conformable definitions. The third rotation matrix P34 is chosen such that the matrix product P34, P23, P12, AP gives 0 at the fourth row, third column. The matrix product P34, P23, P12, AP is explicitly written as follows. We set fourth row, third column element to 0, and we have C3 square plus S3 square equals 1. Solving the two equations for the rotation cosine and sine, we obtain the first iteration sweep yields. Note that the subdiagonal elements are now 0. In the preceding rotations, the matrix elements F1, F2, and so on were not used in decomposition because these quantities do not need to be evaluated or saved. They are not also required for the product matrix AP plus 1 equals our PQP. By ignoring FKs, we do not obtain a full QR decomposition of matrix A, but instead retain sufficient information needed to compute the product of our PQP. The QR decomposition step of this method can be generalized as follows. And where the similarity transformation steps are ordered in such a way that memory allocation is kept to a minimum. Upper triangular matrix is obtained as a result of our P equals the product of P n minus 1 into P1 to AP. Since RP equals the product of transpose of QP with AP, we find transpose QP equals the matrix product of Pn minus 1 into P12. The result is generalized as QP equals the product of transpose P12 to transpose Pn minus 1 n. At this point, there is no need to compute QP explicitly to construct our PQP. After each rotation, CK and SKs can be multiplied. Here the following abbreviations were used. The next step gives where D2, E2, and D3 are modified as follows. The tridiagonal matrix is symmetric, and QP is orthogonal. The matrix product, our PQP, is also symmetric. Thus, the elements of the product matrix corresponding to superdiagonal positions do not need to be computed. We deduce the following steps to construct the AP plus 1 matrix. The eigenvectors can also be simultaneously obtained. Let V be a matrix of eigenvectors, with the jth column being the associated eigenvector of lambda j. To compute eigenvectors, the matrix V is initialized to the identity matrix V0 equals I before the QR iterations. Once the matrix AP is decomposed, the matrix V is improved upon by the following. The eigenvector computations are generalized as follows. Where VIK denotes the elements of the matrix of eigenvectors, and Qn are temporary variables used to overwrite the updates on VIK and VIK plus 1, respectively. The QR iteration procedure is repeated until the subdiagonal elements of AP, IE, EKs are sufficiently small. A criterion for convergence is based on either the relative or absolute error of the eigenvalues or L2 norm of the subdiagonal elements. A real symmetric tridiagonal matrix A, whose eigenvalues are ordered in descending order for a sequence of iterates, AP will converge to a diagonal matrix that contains a sequence of lambda k in the diagonal position, ordered in descending order. As for the matrix AP, diagonal elements approach the eigenvalues, while the off-diagonal elements approach 0, as the number of iterations goes to infinity. The convergence criterion is monitored at each step. The rate of convergence is linear with a convergence ratio of lambda k over lambda k plus 1 in absolute value. The basic QR algorithm presented here converges slowly enough to be competitive, especially when the eigenvalues are clustered together. The advantages of the QR method are: the method presents a simple, elegant algorithm for finding the eigenvectors and eigenvalues of a real, symmetric, full-rank matrix. It gives the complete set of all eigenpairs, i.e., the orthogonal matrix QP, whose columns approach eigenvectors of A, and a diagonal matrix AP, whose diagonal elements approach the eigenvalues of A. It can be used as a direct solver for the system of linear equations. It has been improved by variants having quadratic convergence rates. The disadvantages of the method are: the basic QR method has a linear convergence rate. It may fail when no real eigenvalues exist, or when the eigenvectors do not form an orthogonal basis. It requires excessive memory for large sparse matrices. Its convergence can be slow if the eigenvalues are close to each other. With this note, we conclude this lecture. That is all for now. See you next time with another topic. Bye.